Okay, let's move into our BGP topics. We actually have several different BGP topics that we're going to be talking about, but we're going to start by talking about designing BGP routing and redundancy. We're going to start by focusing on iBGP, our internal border gateway protocol. But I do want to talk a little bit about some of the restrictions about iBGP and why we would need this scalability, these scalability techniques that we're going to be talking about. But throughout the section, we're going to talk about what the scalability issues are for BGP, specifically iBGP. What is a BGP route reflector and how do we implement that? What is BGP split horizon, the loop avoidance mechanism that's built into BGP? How do we use a route reflector as a loop avoidance prevention or loop prevention mechanism? And then we're going to take a look at BGP load sharing designs and then finally wrap up by examining dual homed and multi-homed BGP designs. So we have BGP is a path vector routing protocol, but from the perspective of a lot of the protection mechanisms that it has built into it, it uses a lot of the techniques that we see in distance vector protocols, things like split horizon, where I never advertise a route back out the same interface that I learn about that route on. The limitation specific to BGP is that we have to have full reachability, and iBGP has a lot of limitations in from a design perspective that would prevent us from achieving that full reachability without adding some sort of concentration router called a route reflector. We can also use BGP confederations. We'll talk about that a little bit in this section as well. And we can also extend interconfederation designs by adding external BGP sessions as well. So that's what we're going to focus our attention on in this section here. But before we actually get into those details, what I would like to do is I would like to talk a little bit about BGP itself, right? It's the present interdomain routing protocol that we see on the internet today, Border Gateway Protocol. There used to be another one called EGP, the Exterior Gateway Routing Protocol, but it doesn't exist anymore. There are two modes of operation in BGP. There's external BGP, which is used to exchange routing information between autonomous systems, and internal BGP, which is used to propagate that information within the autonomous system. In a full mesh iBGP configuration, every router has a BGP session with every border router in the autonomous system. Because a full mesh configuration has a large number of iBGP sessions, it doesn't scale very well. And configurations that are based on route reflectors are going to be used for intra-AS, not inter, but intra-AS routing dissemination. Unfortunately, route reflector configurations violate essentially the important correctness properties, including what we call loop-free forwarding and complete visibility to all of the eBGP learned best routes, especially in the face of router and link failures when we see those failures that happen in the network. So what we're going to analyze in this section here is the first to take a look at the BGP algorithm. How do we construct an iBGP session that is correct and kind of more scalable than a full mesh design? We could certainly do that full mesh design. You can see that on the right side there. On the left side, we see a full mesh as well. We have 4 routers, but the number of sessions per router is 3. The total number of sessions is 6. But as I add more routers to the topology, you can see that the total number of sessions kind of goes up exponentially. We add 1 router to the overall topology, right? We add 1 router to the topology, but it creates 4 additional sessions. All right. So this is what we are really trying to accomplish here. We're trying to get rid of the need for that full mesh functionality. The internet itself is made up of lots and lots of different autonomous systems, and they all kind of group together to form the internet. All right, the egress router at the border of an autonomous system uses BGP to exchange routes on an external BGP peering session with the peer router. Each eBGP router picks the best route to each destination, and then it has to disseminate that route to every other external destination prefix, or excuse me, all of the other destination prefixes that it learns to the other routers in the autonomous system. These other routers in the autonomous system obtain that information about all the possible routes to the destination, and they pick their own best choice. All right. The one approach to this kind of intra-AS routing dissemination is to rely on an iGP. And that's pretty typical, by the way. You know, and don't run BGP internally, run some sort of iGP routing protocol like OSPF or EIGRP to propagate the routing information for the destinations within the AS. And then basically we just introduce routes for the external destinations into the iGP, typically through redistribution or whatever. This approach does not work well because a lot of common iGPs like OSPF, like ISIS, like EIGRP and RIP, don't handle the scaling of BGP very well. If we're only doing a subset of routes, that's fine. And we won't have to worry too much about the scaling issue. But the policy propagation in BGP, the number of routes that exist in BGP, might not provide us the opportunity to be able to use an iGP protocol inside of our autonomous system. All right. Now, another approach that's used by some ASs is to eliminate the problem of intra-AS route dissemination by tunneling the traffic. Again, not really the best option. The third approach would be to implement BGP sessions between routers inside the autonomous system. This is what we call internal or iBGP. The designers of BGP proposed the use of a full mesh for iBGP for many reasons. And we'll talk about what those are and why we need to maintain that as we go through the rest of our discussion here. Each eBGP router in the autonomous system, the ones that are at the perimeter of the autonomous system, are going to establish BGP sessions with all the other routers, both the eBGP routers and the internal routers in the network. But whenever we establish a relationship with a router that's in the same autonomous system that we're in, that is called an iBGP peering session, and it's going to still rely on an underlying IGP for reachability and connectivity, but we can exchange the routing information, the network reachability information that we have in BGP by using that iBGP configuration. All right. Now, why would we consider doing a full mesh? Well, it's going to provide things like complete visibility in a sense that for every external destination, each router picks the same route that it would have picked had it seen the best routes from every other eBGP router directly, even though it's not really an eBGP peering relationship. We would also provide for loop-free forwarding in this case. Once we learn about all of those eBGP routes, the subsequent forwarding paths that exist would also be learned, and that would be picked up by all the routers, and we would be able to really kind of decide how we want to route based on that. And then the robustness to IGP failures would be important as well. Route dissemination mechanisms should be robust to prevent issues if a node fails or a link fails or if the IGP path cost changes. Unfortunately, and that's what they're showing you in this particular slide here, a full mesh configuration just simply doesn't scale well. We have n to the n minus 1 divided by 2 plus any additional routers that we have to add sessions. So if you have an ISP or a service provider network that has potentially hundreds of routers, it would require thousands of sessions. This lack of scalability has been a problem with the full mesh configuration for some time. And there have been lots of different proposals on how we can kind of circumvent this problem. The most common technique used today is what we refer to as route reflection. And we'll certainly get into that as part of this discussion. So in route reflection, what we do is we take a subset of BGP routers. They're going to be designated as route reflectors. They're going to provide their best routes to the other routers, which are going to be configured as route reflector clients. In large networks, we use route reflectors and the route reflector hierarchy, but they're kind of normally configured as I don't know, just arbitrary routers in the domain that provide this route reflection service. All right. Now we will talk about that. We'll talk about the concept of route reflectors and how route reflectors work. That's obviously part of our discussion here. And we'll talk about some other techniques that are available as well in this with this scalability. The idea, though, in this case, so the whole point, obviously, in discussing all of this is because the full mesh peering option that we have just really isn't scalable. If we had 50 routers, for example, and the book kind of describes this, if we had 50 routers, that would require over 1,225 iBGP sessions. Again, those are relatively small numbers compared to what you might see in a service provider environment. Now, there are two choices that we have for managing this scalability problem. One is to use route reflectors. Route reflectors modify what we call the classic iBGP split horizon rule and allow particular routers to forward incoming iBGP updates to other iBGP clients or the route reflector clients. And essentially, it's kind of a concentration point, if you will, of all the routes that we're learning within the iBGP domain. The other is to set up a confederation. BGP confederations give us kind of like sub-autonomous systems, if you will, within the overall AS. And then these smaller autonomous systems can exchange information between them by using these kind of pseudo eBGP interconfederation sessions between them. So we're going to talk about both of these options throughout this section here and look at what the benefit is of doing one versus the other. Let's start by looking at route reflectors. All right. We can scale our BGP network by using a route reflector. A route reflector is an iBGP router that is configured to act as a speaker for other iBGP peers in the domain. You can almost think of it like a designated router where we're exchanging link state update information to one router, and then that router is responsible for disseminating that information to the other routers in the topology. Route reflectors get enabled by defining iBGP peers as route reflector clients. The clients actually don't really need any additional configuration. And obviously in this case, the number of BGP sessions drops significantly because the route reflector is the BGP speaker that reflects or re-advertises routes that are learned from other iBGP peers to some of the other iBGP peers in the domain. You can kind of see that in the diagram here. The center router is acting as a route reflector. And it receives information from a route reflector client. It's going to propagate that information to both the route reflector clients and the non-client routers. It is actually a fairly simple configuration. It can be done incrementally. We can define route reflectors as peers, but there is no special configuration that's needed on the clients themselves. Each client router just has to be configured as a client on the route reflector or on multiple route reflectors if we're running redundancy. and then any of the unnecessary peering relationships that we had, if we were running a full mesh, can be removed. And the route reflector clients ideally will peer with those route reflectors only. All right. So we're not reducing completely the number of adjacencies, but we're certainly reducing the adjacencies down to a relatively small amount. I mean, ultimately, when it comes to route reflection, this is a scalable way of disseminating that external routing information throughout the AS. Some BGP routers in the AS, like I said, would get designated as route reflectors. Normal iBGP peers do not propagate the routes learned from one peer to another to avoid those routing loops, but the route reflectors have different kind of rules. That's that split horizon rule that we keep mentioning. Never advertise a route out the same interface that you learn it on, or, in the same direction that you learn it from. A route reflector has two types of iBGP sessions when it gets set up. The client iBGP sessions with some peers configured as route reflector clients, and normal iBGP sessions with non-client peers. So you might look at this and go, well, wait a minute, why would the route reflector send the routes to those non-client routers? Because we have a standard iBGP peering relationship with those routers. And the route reflector clients, we don't actually technically have a peering relationship with. So when a route reflector receives a route from an iBGP peer, it selects the best route by using the rules that we talked about previously, the path selection process, if you will. We'll get into that in more detail a little bit later on as well, what the overall BGP path selection process is. But once that path selection process is done, we have to do one of two things, right? Depending on the type of peer that it is receiving the best path from. A route from a non-client iBGP peer is reflected to all the clients automatically. A route from a client peer is reflected to all the non-client peers, but also to the client peers. Okay? So we still have the split horizon rule in place for our non-client peers, but we don't have the split horizon rule in place for our route reflector client peers. The client peers don't need to be fully meshed. The total number of BGP sessions in this case is much, much smaller than what we would have in a full mesh. Now, typically in a large autonomous system, we do route reflector clustering. That clustering is hierarchical. Every route reflector cluster has one or more route reflectors, typically more than one route reflector. And the other routers in the cluster get designated as clients of the route reflectors in that particular cluster. The clients within the cluster may or may not peer with each other. There could be some sort of hierarchy of route reflectors where you might have a client of a route reflector that acts as a route reflector for other routers as well. So you can create kind of this tiered architecture of route reflectors. All right. Now, one of the things that's important to understand, and I don't know how much detail I want to get into in this because we're not really trying to learn BGP all over again here. It's just like with OSPF and EIGRP, the design class kind of makes assumptions that you know some of these concepts. But with regard to complete visibility, in an iBGP configuration that uses route reflectors, it's important to note that the route reflector reflects only the best route. It doesn't reflect everything that it learns. All right. So the clients themselves don't choose the same routes that it would have chosen had we seen those as maybe eBGP routes, or had we had complete visibility based on a full mesh of iBGP peers. Let's take, for example, an iBGP configuration. Let's say we have a route reflector configured, and the client's configured, and that creates that cluster. The IGP and the iBGP interconnections allow for the communication. Now we have routes that get advertised from the route reflector client to the route reflector. Now each of those clients might be advertising the same prefix. Maybe it's the same destination, but they're learning it from other peers separately. The route reflector is going to choose the best path, and it's only going to reflect what it chose. Now that could be, I guess, potentially an issue. It just depends on the specifics of how that routing information is learned. The property of complete visibility is actually pretty important for predictable routing. If for some reason complete visibility is not available, the system will fail to implement what we call hot potato routing, meaning that network resources are going to be wasted predicting the outcome of complex BGP policy decisions. Is difficult, but it gets a lot easier when you do have that complete visibility, because every router is basically guaranteed to pick up the route it would have picked had it seen all of those external routes learned through eBGP, if it was learning through eBGP. From a loop-free forwarding perspective, route reflectors configurations are susceptible to forwarding anomalies. We can see forwarding loops, we can see deflections, which makes it harder to maintain and debug that as well. At every router, BGP selects only the egress router for a particular destination. The actual forwarding path from that router to the egress is provided by the IGP protocol. All right. So in that situation, you might have some routers on the shortest path to the egress could choose a different egress for the same external destination, meaning that the packets would actually get deflected along that forwarding path. We're kind of getting into the weeds a little bit with this discussion. I don't think that's the intent necessarily of this particular topic, but it is an interesting concept. And certainly when I get into advanced routing and the CCIE enterprise discussions, we talk about this quite a bit. All right. But if you are going to select a route reflector in your topology, you need to select the best candidate for that role. We configure the route reflector functionality on the route reflector. We don't have to configure the clients, but keep in mind, again, we are now eliminating the need for the route reflector clients to actually have a peering session with the route reflector itself. All right, at least directly. Another option that we have is to configure BGP confederations. Basically, in a nutshell, we're creating subdomains of our larger autonomous system. We partition the autonomous system into these sub-autonomous systems, and then we create relationships between those different sub-autonomous systems. And that's how we get rid of or get around this iBGP full mesh configuration. So that's a really useful option. We'll see more about confederations a little bit later on. Actually, I don't think we get into it too much in this particular class, but you can understand why this gets rid of the reliance on a full mesh of iBGP speakers, because now we're creating eBGP peering relationships. The ASs use these sub-autonomous systems to scale the overall AS. The outer AS is what we call the confederation AS, and all of the inter-autonomous systems are what we call sub-autonomous systems. And each sub-autonomous system has its own private autonomous system number. We can actually also implement route reflectors within the sub-autonomous system to get even more scalability within that autonomous system as well. Confederations are actually going to insert information into the AS path attribute. We'll talk about the attributes a little bit later on when we get into essentially how BGP functions and the decisions that it makes for routing. But the basic idea with a confederation is to divide your normal BGP autonomous system, which is relatively large and lots of routers, into these sub-autonomous systems. The outer, or that containing AS, that confederation AS, is what's visible to everybody else in the rest of the world. And then we manage those sub-autonomous systems internally. And those sub-autonomous system numbers are typically going to be chosen based on the private AS range, 64,512 through 65,534. All right. Now, the BGP confederations contain that full mesh requirement because we are able to establish external BGP sessions between those sub-autonomous systems. And we can now use all of the eBGP peering rules that we normally wouldn't be able to use with the iBGP peering relationships. For example, split horizon doesn't exist with eBGP peering relationships. We can advertise routes from one eBGP peering session to a different eBGP peering session without any problem. All right. They have a table here that kind of describes some of the techniques. Loop prevention, for example, is part of the AS confederation set. We actually have a loop prevention technique that we'll talk about, or section we'll talk about later on. Breaking up the single AS. Yes, we do that with sub-autonomous systems. In route reflector technology, we use clusters or route reflector clusters. Although we aren't technically really breaking up the AS into sub-autonomous systems, we're just maintaining that large autonomous system with these different route reflector clusters. For redundancy, we can have multiple connections across the different sub-autonomous systems with confederations, or we can have multiple route reflectors in the route reflector technology. We can establish external connections anywhere in the network in both cases. It doesn't change how we deal with eBGP peering relationships. We have a multi-level hierarchy. With confederations, we would implement the sub-autonomous systems with nested reflectors inside of those sub-autonomous systems to get that hierarchy. In route reflectors technology, we would have maybe a primary route reflector that might point to a secondary route reflector that might point to a tertiary route reflector, and we can have that nested hierarchy in that regard. Policy control is something that's established typically on an external router. So it would be on a router that's creating some sort of eBGP peering relationship. When we say policy control, we're talking about the inbound and outbound policy rule sets that BGP can apply to routing decisions. And very rarely do we apply those rules internally within our autonomous system. It's usually rules that we're applying. We're either trying to influence how somebody routes to our autonomous system, or we're trying to influence how we leave the autonomous system, and that's typically done on an external router. Now, with a route reflector scenario, that would be a traditional eBGP router. With a confederation, because we have these sub-autonomous systems that actually have different autonomous system numbers, we're actually creating those eBGP peering relationships within the primary confederation domain, right? The primary confederation AS. So we can actually create those routing rules internally within our organization, and we don't need to only implement those policies on eBGP pairing relationships that go to other customer networks. Migration, route reflectors, pretty easy to do. The configuration is relatively simple. We only configure the reflector, and then the clients don't really get any configuration. With confederations, it's obviously a lot more complex because you're essentially creating kind of mini-me BGP domains, right? Autonomous systems. So we'll get into the route reflector concepts in the next section. We'll talk about the BGP split horizon rule and how we can use this stuff for loop prevention mechanisms. And then we'll wrap up this section. So the next thing we want to talk about in this section here is about the route reflector terminology. We've kind of described what the concept of a route reflector is and the purpose of having a route reflector in our iBGP domain. And so now what we want to talk about is really kind of some of the different terminology and some of the different techniques that we can use to deploy these route reflectors. The concept of BGP, obviously with iBGP speakers, is that when we're peering with BGP between routers within the same AS, obviously that's an iBGP relationship, there are different restrictions that we have with those types of relationships as opposed to some of the restrictions that we don't have with eBGP peering relationships. And most of it has to do with the fact that BGP does operate kind of like a distance vector routing protocol. Even though it is not technically distance vector, it is a path vector routing protocol. But we don't necessarily have a complete picture of the topology because it is an external autonomous system routing protocol, which means that we understand what's happening within our own internal routing domain, but we don't necessarily understand what's happening in other routing domains. So one of the rules to avoid routing loops, and we mentioned this previously when we started this whole discussion, is that any routes that are learned via iBGP should not be advertised to other iBGP peers. So if I learn a route from an external BGP peer, I can reflect or re-advertise that route to an internal BGP peer, but that's the extent of where that routing information can go. And this is called the BGP split horizon rule. And we mentioned this yesterday as we were going through our discussion that for all the BGP routers internal to the autonomous system to learn all of those external routes from our external sources, we would have to establish an internal BGP peering with all of the other internal BGP routers. So basically creating that full mesh of interconnected iBGP peers. If you have a small number of routers, not a problem, right? 10 routers or so, you might need what, about probably 45 or so sessions. 15 routers, you would need over 100 sessions. So as the number of routers increase, so does the number of BGP sessions that are required to establish a full mesh of iBGP peers. So the solution isn't scalable, right? And we mentioned this a couple of different times. It's just not really feasible to have a full mesh of iBGP peers, especially as you add more and more routers. In addition, those iBGP peering sessions, because BGP is an application layer protocol, it operates over TCP, that could consume quite a lot of bandwidth. All right. So a more scalable option is to consider the implementation of this route reflector technology. We configure routers as a route reflector, and by definition, they are allowed to propagate routes that are learned via iBGP to other iBGP peers within the autonomous system without violating that typical behavior. So let's assume that in this particular topology here, that all the routers are already running BGP. And we don't have a whole lot of routers in this particular topology, but let's assume that we're also dealing with a very large network that might potentially consist of hundreds of routers, which would create a very significant and large internal BGP mesh. Tracking hundreds of sessions in a network would just really not be feasible. So instead of establishing an iBGP peering relationship with each and every router in this internal BGP mesh, routers establish iBGP sessions with the route reflectors only. The route reflectors basically represent a central focal point for all of our iBGP sessions. We form a cluster together with the clients, other routers that are part of this kind of internal BGP mesh. Now, because the route reflector propagates the iBGP routes to the other iBGP peers, a full mesh of peers, meaning peering between all the clients in the entire domain is no longer needed. This is obviously going to save a large number of iBGP sessions that would normally have to be maintained if I did not have this route reflector concept. So, this is kind of a repeat of what we had talked about previously, right? But I want to make sure that we solidify this understanding. We set up a route reflector, we set up route reflector clients, and then we have non-clients, which are basically just iBGP peers that are not configured under the route reflector configuration. Each route reflector is also a non-client of the other route reflectors in the network, so they don't actually form a peering relationship together. Now, the route reflectors themselves have to be fully iBGP meshed with non-clients, because essentially a non-client is just a normal iBGP speaker that we're establishing a relationship with. A client, on the other hand, is any iBGP peer that the route reflector reflects routes to. And that's based on the configuration on the route reflector router that we set up. Now, to configure a route reflector client on the route reflector, we have to specifically specify that client as part of our BGP configuration. We don't really talk about specific configurations in this class, but I will kind of mention briefly what that configuration looks like. All right, so we can propagate these routes throughout the autonomous system based on this relationship to the route reflector. And the route reflector basically replicates or reflects the routes from an iBGP router to all of the other iBGP router. It does, I guess, technically in that sense, violate the typical behavior of what an iBGP router does. But that's by design, right? And when I say violates the behavior, we're talking about violating the no split horizon rule that we have by default in BGP. Now, which router we decide to use as a route reflector really is up to you. It is kind of recommended, I would say, that you choose routers that have, I wouldn't say a vast amount of resources, but certainly significantly more, or at least more resources than your typical routers in the domain, because we are going to have some additional overhead and some additional processing requirements for the route reflector. You have to be cognizant, of course, of what that route reflector is doing, who it's building a relationship with, and who it's communicating with, both the clients and the non-clients, because if you don't configure it correctly, you could actually create instability within the autonomous system. We could actually end up with a misconfigured route reflector that actually sends routes from one cluster and then returns those routes to that same cluster later on. All right. In addition, it would be highly recommended that you also implement a backup route reflector. And we can create this redundancy by simply having a secondary route reflector that is defined. So if that primary route reflector fails, then the secondary route reflector could certainly take over for that particular function, if you will, right? Route reflectors still have to be fully meshed, like I said, with the non-clients. And that's kind of what the, not in this particular diagram. The blue lines represent the relationship with the clients from one route reflector, and the red lines represent the relationship with the other route reflector. But for non-clients, it would just be a standard iBGP peering relationship. And by the way, the the split horizon rule would apply in those types of relationships. So if you only deploy one single route reflector, obviously you would have a situation where you would have a single point of failure, because the route reflector clients don't have any peering relationships with each other. They're only peering with the route reflector itself. So in this iBGP network, based on route reflectors, we rely on those route reflectors to be able to disseminate routing information and to be able to establish convergence in the network. So obviously, having only one route reflector in the network is not really that recommended. So we want that redundancy, both physically and logically. The clients themselves will establish BGP sessions with multiple route reflectors by using these redundant physical paths. Obviously, we don't have to. iBGP peering relationships can be logical, unlike most other like IGP routing relationships where there's a physical relationship as well as a logical relationship. But in BGP, iBGP peering relationships are logical. So we would want to make sure that we're somehow establishing that relationship over maybe a different path, or at least have redundant paths to be able to reach those route reflectors. Both route reflectors in this particular case, they're going to receive the same iBGP updates from their clients. They will both reflect those updates to the rest of the clients, and then both route reflectors will also get updates from the full mesh and reflect those updates to their clients as well. We're talking about the full mesh of non-client routers that we have. So each client in this case will actually get 2 copies of all the routes. So you need to, make sure that you establish the appropriate BGP policies. We haven't talked about what those policies look like yet. Weight, local preference, AS path, etc., all the BGP attributes to influence how we choose a particular path, because again, we could introduce suboptimal routing, or we could create a scenario where we're creating a loop in the topology. All right. There are other issues that you have to be aware of with these route reflectors. Like I said, the implementation of a route reflector does pose a risk of creating a loop in the routing domain. If you have a poor configuration, it is possible that the route that's sent from one cluster returns to that same cluster. Now, in order to maintain loop prevention with the implementation of these route reflectors, we use an optional attribute called an originator underscore ID. So when we reflect an iBGP route from one iBGP peer to another, the route reflector appends this originator underscore ID attribute together with the cluster ID to that particular route. And that carries the router ID and the originator ID, originator ID carries the router ID of the originator of the particular route. If I receive a route with the originator ID set to my own router ID, that's when I would probably ignore that particular route. So we still have some loop avoidance mechanisms that exist in the configuration, but we still need to be cognizant of what we're doing in this topology. So before you can configure a route reflector to peer with different clients, the first thing you need to do is, of course, establish the adjacency with those clients. So that would be a standard BGP configuration using the neighbor remote AS command. So that would be step number 1. Okay. The clients themselves should also be configured to peer with the route reflector. And again, it's no different than any standard BGP configuration. It looks exactly like a standard iBGP configuration. You identify the router autonomous system and you specify the neighbor with the remote AS. On the route reflector, we add a second command for that particular neighbor. And it's basically just neighbor x.x.x.x route-reflector-client. And that's it. It's a really, really simple configuration. Very, very easy to configure. And that eliminates the need, of course, to have, say, client A and client B having an iBGP peering relationship with each other, because we are using this route reflector configuration. All right. Now we do have the option of also creating route reflector clusters. Route reflector clusters are what prevent these routing loops if I have a redundant route reflector design. And as I mentioned, in this particular case, we have something called the cluster ID that is unique within that autonomous system. The redundant route reflectors and their clients form that particular cluster. And then within the cluster, each client peers with all of the route reflectors. So we can see in this particular case, we have cluster 1 with 2 different route reflectors, cluster 2 with 2 different route reflectors for the redundancy within the cluster. The route reflectors from the different clusters have to be fully meshed with each other because they basically become essentially iBGP peers, regular iBGP peers. We can't do route reflection from one cluster to another. We have to just create this full mesh between the route reflectors from all of the different clusters. Now, the clients will peer with all the route reflectors within the cluster for redundancy. And then the route reflectors from different clusters, like I said, have to be fully meshed with each other. That's what the green lines in this particular diagram represent. There are some exceptions to that rule. We don't need to get into the specifics, but there are some exceptions to that rule. Hopefully, if you get a chance to take one of the more advanced routing classes or BGP classes or whatnot, you'll learn about those exceptions. But we're going to continue on here. The cluster ID number is what uniquely identifies that cluster within the autonomous system. Now, you can explicitly configure that cluster ID if you want. If it's not explicitly configured, the router ID of the router is used as the cluster ID. And if you recall from maybe earlier classes you've taken or only from your basic knowledge, router IDs uniquely identify a router within the autonomous system. They can either be manually configured. It'll be the highest active loopback interface on a router. And if we don't have any loopback interfaces, it will be the highest active physical interface on the router. And of course, every router is going to have a physical interface because otherwise it wouldn't be a router. All right. But this cluster ID configuration is pretty critical. You can use the BGP cluster-ID router command to set the cluster ID. If that cluster ID command is not used, then the router ID, like I said, is going to be used. When we have all route reflectors in a cluster share the same cluster ID, this is what we refer to as a redundant cluster, because the cluster ID is identical between the route reflectors. The routes that actually get exchanged between those route reflectors get discarded because of that cluster list concept that I talked about previously. Meaning that we see our own cluster ID in the information that's being shared. In the right side of this particular diagram, we have a cluster ID on the left of 10.10.10.254. And on the right side, we have a cluster that's configured without the cluster ID. We have an IP address or the router ID, for the bottom left route reflector is 10.10.10.1, and the top right route reflector is 10.10.10.2. Now, to prevent loops, the route reflector is going to add that router ID of that reflector to the cluster list of the routes that it actually reflects to its iBGP speakers. That route selection process is modified to include the idea that we are going to look for the length of that cluster lists and almost like an AS path attribute where the shortest AS path is going to be preferred. In the case of cluster lists, a route with a shorter cluster list is going to be preferred over routes that have a longer cluster list. All right. We can also implement non-redundant route reflector clusters, non-redundant in non-redundant configuration. Basically, the client routers have a single physical connection to the route reflector. router, and this creates that what we call a non-redundant cluster. This is a single point of failure. Obviously, we talked about that because if that route reflector fails, there is no configuration of a secondary route reflector, and there's no iBGP session with a secondary route reflector from the client's perspective. So they're no longer going to be receiving network layer reachability information because the route reflector is a dedicated route reflector and it no longer exists. I don't know that this is this is the best way to implement this type of configuration. Obviously, we want to have redundancy built into the topology, but it is possible. We can configure a single route reflector. All right. We can also create what we call a hierarchical route reflector design. We kind of see a representation of that right here, where we build actually route reflector clusters in kind of a tiered architecture or hierarchy. With this hierarchy, we have a router that serves as a route reflector in one cluster, but it acts as a client in another cluster. You can kind of see that almost like depicted like almost like an area border router. The three routers kind of in the middle of the diagram here are acting as a route reflector for the domain on the bottom, cluster 22, but they're also acting as clients in cluster 27. All right, so basically in this particular configuration, we have iBGP sessions on a route reflector. We have to configure those sessions to reach a client in order for us to be able to circumvent or get around the iBGP split horizon rule. And then all of the other iBGP sessions that are configured on the route reflector are part of the full mesh design. Remember, from one route reflector to another, we have to have a full mesh. And we see that in cluster 27 for the route reflectors that are servicing cluster 22 and cluster 10. Happens to be in cluster 22 that we have a redundant route reflector configuration, and in cluster 10 we have a single route reflector configuration, and then in cluster 27 we have a redundant route reflector configuration. You could see how this would be beneficial because we're now able to pass information from one cluster to another. But again, we have to be very cognizant of information being looped around or created, and that's where the cluster ID and cluster information that I talked about previously comes into play. It's a little bit more complicated, obviously, than what we're discussing in this section here. This is a topic that we could easily spend 10, 15 hours on discussing good route reflector design and route reflector implementations. But again, that's not really the purpose of this particular course. Our idea here is to get a general understanding of what these concepts are so that we can make decisions on, general design decisions on how we decide to implement our overall architecture. The cluster list attribute, as I mentioned before, plays a pretty significant role in the hierarchical design. We want to make sure that we have loop prevention mechanisms in place. We also want to make sure that we're selecting the most appropriate path to reach a particular destination. So a cluster list attribute is significant for that, especially for the loop prevention piece. The cluster list will be longer as I reflect routes each time. So if a route comes back to the reflector that had already reflected that route, it's going to get dropped because that indicates that there is a loop in the topology. So this diagram is really kind of giving us an example of this hierarchical structure. The first level of the hierarchy reduced the original full mesh of 12 routers. All the routers that we see on the diagram basically here to a full mesh of 7 routers, which are the lower 3 route reflectors and the upper 2 route reflectors and 2 clients. That's the 7 routers that we see basically in cluster 27. All right. So that's the top level. And then the second level of route reflector clusters is built to create that cluster 27. And then we reduce the number of full mesh requirements. So basically, the clients all across the bottom of the diagram here don't have any iBGP peering relationships with each other because they have those peering relationships with the route reflectors themselves. If a client at the lowest level receives an eBGP update, we'll say from the right side here, we get an eBGP update from this router on the right, that information is going to be sent up to the route reflector client. And of course, at a minimum, it's going to be reflected to the other client in cluster number 10. But additionally, that information is going to be reflected to the other reflectors. They're not acting as route reflector clients. They're just basically fully meshed iBGP speakers, but they'll still receive that information. All right, and in turn, that information is then going to be sent to those clients as well. But you can see where this can get rather complicated. The relationships that we have between the route reflectors themselves are normal iBGP sessions. So the split horizon rule would apply in this particular case. But as I move to, say, cluster 22, we're reflecting information down to the clients here. They're going to receive 2 copies this way as well and this way as well. They're going to receive 2 copies of the information. So they need to make sure that they have a way of selecting which one is more preferred. And that's kind of where we don't really get into that discussion in this particular part of the course because that's really more of an implementation and configuration discussion. But it is something to consider. Okay? All right. So all of this stuff that we've been talking about is related to the fact that we have this BGP split horizon rule. Split horizon is a general rule that says, never advertise something out the same place you heard it from. Well, in the case of BGP, this is a pretty critical concept, right? All routers inside of an autonomous system have to make a routing decision in a consistent way, right? They have to have access to the same routing information with the same attributes in order to come to, I guess, the same conclusion about what exit point of the autonomous system to use. In other words, the BGP attributes should not be changed within the autonomous system itself because we all need to make essentially the same educated decision on how we're going to leave that autonomous system. There is an attribute, and we'll talk more about the attributes in a little bit more detail later on. There is an attribute called the AS path attribute that is not changed over an iBGP session, which makes sense because we didn't cross an autonomous system boundary. But the AS path attribute is a primary way of detecting not only what the best path is, shortest AS path, but also to detect routing information loops. All right. Specifically, if a router encounters its own autonomous system in the AS path of a BGP update that it's receiving, it will basically just silently ignore that information. Because the AS path is modified by BGP speaking routers, but only on eBGP sessions, this loop avoidance mechanism or loop prevention mechanism is very useful when it comes to routing between autonomous systems, but it's not as useful when it comes to routing within the autonomous system. So routing information loops within the autonomous system get prevented by this iBGP split horizon rule. Routing information that's received through one iBGP peering session is never going to be forwarded to another iBGP neighbor. So that's a little bit different than kind of a traditional split horizon rule where we say, you know what, don't ever advertise what you receive back out to the person you received it from. It's a little bit more kind of critical than that, because now we're saying not only are we not going to advertise out the same towards the same direction that we received the information from, but we're not even going to advertise to other iBGP speakers in the system. We can certainly continue to forward routing information over to our eBGP peers, but because of the BGP split horizon rule, no router can relay iBGP information within the AS. They must be directly updated from the border router that receives that eBGP update. And that is where this idea of the full mesh comes into play. All right. Now, all of this is based on the fact that in iBGP sessions, the AS path attribute isn't modified when we propagate advertisements to another iBGP peer. Only when we're sending advertisements to our eBGP peers is the autonomous system number of the BGP speaker added to that AS path attribute. It's always kind of prepended, if you will, to the overall AS path. So the real problem arises if the originator node withdraws the BGP advertisement, and if we don't have any control mechanisms in place, that node could actually be fooled by a copy of the advertisement that it might receive from another node, and then re-advertises it, and that's where the loop comes into play. So as a result, in the autonomous system, we would still be representing an advertisement for a prefix that might not even actually exist anymore because the prefix is getting duplicated. All right. So in interior routing, as the book states here, a split horizon route advertisement is a method of preventing routing loops in a distance vector routing protocol by prohibiting a router from advertising a route back onto the same interface from which it's learned, right? We mentioned that a couple of times already, all right? And that's a traditional distance vector concept. RIP and EIGRP, IGRP all have a similar concept. But again, that's not specifically what we are talking about in this particular case, because we're talking about going from one iBGP speaker to another iBGP speaker. We already know that this split horizon rule prevents routing loops in BGP, but eBGP and iBGP kind of treat this split horizon rule differently. eBGP always relies on that AS path attribute to be able to identify a routing loop. If I see my own AS in the AS path attribute, I've already known that, hey, I already originated this route, and now I'm seeing my AS again in the AS path. That means that somehow this information has come back to me, and I can go ahead and ignore that information because it's clearly been looped. But the rule that we have for iBGP, which is the split horizon rule, says, you know what? You will never re-advertise a route that you learn from one iBGP peer to another iBGP peer. Now, that's not to say that I can't repropagate routes, right? As long as the route comes from an eBGP speaker, I can reflect, well, I shouldn't use that term. I can essentially send a BGP update for those prefixes that I'm learning from an eBGP peer. There's no restriction for that. All right. So, like I said, eBGP relies on the AS path attribute, and iBGP relies on this strict split horizon rule. All right. So in the diagram here, we see that we have a iBGP peering relationship in AS 65100. Actually, let's start with where are we starting with here? So it looks like we have an eBGP peering relationship between 65100 and 65200. We have an eBGP peering relationship between 65200 and 65300. And we have, so we advertise the route. Let me get my pen here. We advertise the prefix 10110, and we prepend our AS path or our AS autonomous system information based on the AS path attribute. Okay, fair enough. And we're certainly allowed to repropagate that information to the next autonomous system. And notice that 65200 is added to the beginning of that list, indicating that now we have to go through 2 autonomous systems to reach that destination. And then if that somehow is propagated back to AS 65100, it's saying, you know what, I see my own autonomous system in this list. I'm going to reject that information because it's clearly been looped back to me, right? And that's where we can identify or create this loop prevention mechanism with eBGP relationships. All right. They're not really describing in this case the iBGP split horizon rule, but there's really nothing to describe. If I receive a route from one iBGP peer, I simply don't advertise it to other iBGP speakers. All right. So as any BGP route, the route needs to be the best to be reflected. We talked about that concept actually when we were talking about route reflection. We don't reflect all of the routes. We only reflect the routes that we actually choose to use. And that's a pretty typical kind of distance vector concept. The same thing goes with EIGRP. If I'm learning about a route in EIGRP, if I'm learning about a route from multiple sources in EIGRP, I'm going to choose the best route, and then I'm only going to advertise that choice to my upstream neighbors. All right? But the bottom line is, if I receive a route from an iBGP, eBGP peer, in this case, we've got the 10.1.1.0 subnet being advertised through an eBGP relationship, no problem. We're going to have the AS path attribute. The AS path or AS is going to be added to the route, and we're going to learn that route, no problem. And in turn, I can then advertise that to my downstream iBGP peer. Okay. But that's because it came from an eBGP peering relationship. So there's no restriction in re-advertising a route that I learned from an eBGP peer to another iBGP speaker. But that's where it stops. Because I learned that route from an iBGP peer, Split Horizon says do not advertise that route to the next router. All right. So what we would have to do is we would either have to create this route reflector scenario, or we would have to set up an iBGP peering relationship with all of the routers. So we basically have our 3 routers here. They would all have to have a peering relationship with each other. That creates that full mesh, if you will. That's what the black lines in this particular case represent. They represent the peering sessions. So I can advertise the route one time from an eBGP speaker to another iBGP peer, but I can't do it the second time. We don't have a route reflector in this case, so router 2 advertises the route that it receives from the eBGP peer into the iBGP session. The route gets to R3, but it does not advertise it to R4 because of the split horizon rule. The only way to get it to R4 is if we set up a peering relationship between R2 and R4. Now, in this particular case, that's not really an issue, right? We don't really have a whole lot of routers. Having a full mesh in this case is probably, adequate to solve the problem. Now, if R2 was configured or as a route reflector, and R3 and R4 became route reflector clients, well, in this case, that would basically be the same thing as creating a full mesh because we only have 3 routers in the topology. But the route would definitely get learned in that particular case because it would reflect the route to the clients within the cluster, as well as all non-clients that just have standard iBGP peering relationships. And then the route reflector takes over that role of disseminating that information to the clients, passing along that information. As I mentioned before, if a route reflector receives a route from a non-client, it reflects that route to the route reflector clients, but not the other non-clients. But that makes sense, right? I mean, that's kind of your standard iBGP split horizon rule. A non-client is just a standard iBGP peer, iBGP speaker. So yes, if I receive a route from a non-client, it makes sense that I would not reflect that route or even propagate that route to other non-clients, because that is by definition what the split horizon rule is. Okay. So the last thing we have here is this table that kind of represents kind of the combinations of peers and how the split horizon rule applies to them. So if I get an incoming update from an eBGP peer, I can forward that to everybody. There's no restriction to that. I can send it to my iBGP neighbors. I can send it to my eBGP neighbors. If I get a route from an iBGP peer, I can only send it to eBGP peers. I can't send it to other iBGP peers. If I have a route reflector and I receive a route from an eBGP peer, there's no restriction, again, for how we can forward that information to other routers in the domain. If I receive that route from a non-client iBGP peer, that's no different than receiving it from a standard iBGP peer, and so I can only send that information over to eBGP peers and clients, but not other non-clients, basically other standard iBGP routers. If I receive a route from a client iBGP peer, I can send that to everybody, right? So, because if you think about it, that would be a scenario in which the clients are acting as kind of like, I don't want to say that they're eBGP, but they kind of act like that in a sense that it's safe to repropagate that routing information to other clients. If I'm a client and I'm receiving a route from an eBGP peer, basically I can forward that to anybody. Okay, there's no restriction actually on updates coming from eBGP peers, and we can see that in all three scenarios. We can send that information to everybody. If I'm a client and I'm receiving information from an iBGP peer, again, I have that split horizon rule protection, so I can only send that information to an eBGP peer. Make sense? All right. I mentioned this already in one of our previous sections here, but I want to talk about this again because this is really important. How do we prevent loops with route reflectors? Every time a route is reflected, the router ID of that originating iBGP router is stored in the originator ID BGP attribute. They mention that down here. Attributes that are used for loop prevention include originator ID and cluster list. And I mentioned this again previously when we were talking about this, maybe 20 or 30 minutes ago. But a router that is receiving an iBGP update or an iBGP route with the originator ID set to its own router ID is going to ignore that particular route. Very, very simple concept. The BGP path selection procedure gets modified to also take into account cluster list and originator ID. And like I said, the cluster list is going to be used primarily almost like an AS path attribute, meaning that we're going to select the path with the shortest cluster list and so on. When a route is reflected, the route reflector will set that originator ID BGP attribute. That happens to be make sure I say this correctly, a non-transitive optional BGP attribute. We'll talk about what transitive and non-transitive attributes are and optional and mandatory, or what we call discretionary and mandatory attributes are a little bit later on. But this is the originator ID is a non-transitive optional BGP attribute to the router ID of the peer that it received the route from. Okay? Any router that receives a route with its own router ID in the originator ID suppresses that information. It basically silently kind of ignores that information. The BGP path selection rules get modified, like I said, to select the best route where a router might receive a reflected route and non-reflective routes, or even several reflected routes. We talked about that concept where we have redundant route reflectors within a cluster or redundant route reflectors. It's possible, well, actually probable, that the clients would receive multiple copies of the same information because they're receiving it. We don't have like an active and passive route reflector. We have two route reflectors that are basically duplicating the information. Now, first and foremost, we're going to use our traditional BGP path selection parameters. Things like weight or local preference or origin or multi-exit discriminator. Those are all going to be compared first. All right, and we'll get into those BGP attributes a little bit later on. If all of those parameters, for some reason or another, happen to be equal, any routes that are received from eBGP neighbors would always be preferred over routes that are received from iBGP speakers. All right. Now, if I receive two iBGP routes, which in the case of a route reflector, a redundant route reflector scenario, that can happen, the non-reflected routes, routes that actually don't have the originator ID attribute, are always going to be preferred over reflected routes. We do that because we kind of assume that those non-reflected routes come from a better source of information, more direct source of information than the reflected routes themselves. The reflective routes, let's say I get two iBGP routes from a route reflector. In this particular case, the routes with the shorter cluster list are preferred over routes with longer cluster lists. If the additional route reflector oriented selection criteria doesn't get us to the point in this particular case of making a decision, then we follow the rest of the traditional BGP path selection rules. So it's important to understand that if I'm adding route reflectors or I'm configuring route reflectors in my environment, that it is going to change the overall BGP path selection process. All right. So as we mentioned, there are attributes that are added. The originator ID, which is the router ID of the originating router. The cluster list, which is a sequence of cluster ID values, basically the reflected path or the reflection path. A route with the originator ID that is set to receiving the router ID would be discarded if, as a loop avoidance mechanism, obviously, we talked about that. Shorter cluster lists are always preferred. And in that case, the cluster ID becomes kind of obsolete in that sense. The cluster list attribute also offers a loop avoidance mechanism in this particular case if I have multiple route reflectors that reflect the route where there might be kind of this hierarchical structure of route reflectors in our network. Basically, the cluster list is very much like a autonomous system or AS path list. It's a sequential list of cluster IDs, which prepends the router IDs or the cluster IDs if they're actually configured. Generally, we would have cluster IDs configured, but again, if a cluster ID is not manually configured, we would end up having to use the router IDs. But basically, it's just a list of all the route reflectors that have reflected the route along the way. So we can look at that reflection path and the route, and you know what reflectors the route has passed through. Again, if I find my own router ID in that cluster list, I would discard that as a possible loop. So the process, like I mentioned before, is to use the traditional BGP path selection process, weight, local preference, origin, med, etc., and then we go down the list. All right. Now, if I have a single cluster, loop avoidance is a little bit simpler. When a route is reflected, we add the cluster ID to the cluster list in our single topology. And when the route is reflected, that information gets added we simply identify that route reflector based on that cluster ID or router ID. If we take a look at the example here, we're using a single cluster with two redundant route reflectors. They're configured with an identical cluster ID of 10.10.10.254, which makes sense in this case because I don't want information from route reflector 2 being duplicated to route reflector 1 and so on. So we can send the information to our clients. When route reflector 1 sends an update to route reflector 2, we look at the cluster list and we find the cluster ID matches, so we discard that particular route. And the vice versa would happen if I went from route reflector 2 to route reflector 1. All right. What if I had overlapping clusters? In an overlapping cluster scenario, each route reflector has a different cluster ID, so we can actually exchange routes between the route reflectors. On route reflector 4, routes from client B are preferred because the cluster list is going to end up being shorter. Basically no cluster list because it's not coming from a route reflector. And then maybe routes that are reflected from router 3, right? Because we're going to add the 10.10.10.1 to that cluster list, and we'll select router B or client B as the destination. So with overlapping clusters and two route reflectors, if they have router IDs set individually, that puts them basically into different clusters, but they still share a common list of clients or common supported route reflector clients. So this is probably going to be the preferred scenario when we're trying to configure redundant route reflectors so that we can ensure that we're using or selecting the best possible path to reach a particular destination. I mentioned before already a few times some of the issues that can come up with that can come up when we're dealing with route reflectors, and particularly when we're dealing with redundant route reflectors. Number one, clients do not have sessions with all reflectors in the clusters. That could be an issue, especially if we're trying to configure a redundant scenario. We may not receive all of the iBGP routes because, again, I don't have a relationship with the other iBGP speakers in the topology. I only have a relationship with the cluster, the route reflector cluster, or route reflector, I should say, not route reflector cluster. So if I don't have a relationship with a particular route reflector, any routes that are being sent to that route reflector obviously are not going to be learned by me as a client. All right. Clients have sessions with all the route reflectors in several clusters. The issue here is that we're going to receive duplicate copies of the same route. Now, it's not necessarily a bad thing from a routing perspective. We would still use our routing decisions and our algorithm to decide what the best path is in this particular case, but it is going to require more resources and more information. Clients have iBGP sessions with other clients. So these would be kind of like non-route reflector clients that we have iBGP sessions with. It's possible that other iBGP or peer has a relationship with a route reflector. So it's receiving a copy of information, and I'm receiving the same copy of information from another route reflector, or maybe an eBGP peer in this case it would have to be. Because if it was an iBGP peer, even if it's a route reflector, we still wouldn't forward that information because of the non-client status and the BGP split horizon rule. So it's an eBGP peer. Maybe that eBGP peer is sending information to the route reflector. The route reflector is in turn sending it to the iBGP client, the route reflector client. and that iBGP peer also has a relationship with that eBGP peer directly, so it would also send the same information over to the the standard iBGP peer, because we're not breaking the split horizon rule in that particular case. Modification of the route BGP attributes on route reflectors before reflecting. In this case, because the attributes are how we make decisions on how we're going to route, this can definitely lead to suboptimal routing. We have to make sure that our route path selection process takes into account these modified attributes. All right. So we'll wrap up our discussion of BGP by going through some of the different options for load sharing. Single homed versus dual homed versus multi-homed, and so on. Obviously, when it comes to BGP, we're trying to connect to external routing domains, and we have options when we're connecting to these external routing domains. But each of these options have a requirement or will generate specific design requirements, primarily within the scope of how do we choose the best path, right? Which ISP are we going to choose to route to? Can we influence how the ISP chooses to route to us as well? Certainly the single homed BGP connection is the easiest one to understand. We have a single relationship, BGP relationship, and only one ISP. So there's not a whole lot of deciding here. We only have one way to route in this particular case. But in this case, we're probably going to just simply receive a default route from the ISP. There's really no reason to get BGP routes from the ISP. And then we can decide if we're going to use PI addresses or if we're going to use PA addresses within our enterprise. PI address is what we call a provider independent address space, meaning that basically we are the service provider for that address space. It's not address space that's being routed to us. It's address space that we own and that we're originating to the internet, meaning that we basically went to a regional internet registry and we got our own IP address space, and we are now advertising that address space as the service provider for that particular address space. Provider assigned address space is more of a traditional kind of internet-based ISP assignment where the provider is routing some address space to your destination, but they're the ones that are actually advertising that address space to the rest of the world. And they, I wouldn't say own it, but they're certainly the ones that manage that address space. All right. Also, we would use our own autonomous system number in this case, especially if we're doing provider independent address space. We would have to have some sort of public ASN to be able to advertise or to originate that address space in the internet. Obviously, no redundancy in this design, certainly at the provider level. Okay. If we need only a default route pointing to the ISP, then a static route would probably work. And then the provider would need to create some sort of static route pointing back to your network, and then redistribute those static routes into their own protocol so that the rest of the people on the internet know how to reach that destination. BGP is not necessarily maybe the best choice in this particular case. There's really no need to even run a BGP scenario here because we're basically using static routes to route in and route out. It's only when we have multiple ISPs and we need to control how the traffic is entering our autonomous system and how the traffic is leaving our autonomous system is when we need to have this multi-homed scenario. All right. And that's where we talk about the dual homed versus multi-home scenario. So let's take a look at that. In a dual home scenario, we have essentially two connections to the same ISP. Now that could be from a single router, which is depicted in this diagram, or it could be from two routers within our enterprise. It will change, by the way, how we decide what attributes we decide to use to leave our autonomous system though. For example, a single router, we may use the wait attribute to decide how we're going to leave our autonomous system, Whereas if I had a 2-router dual home scenario, going to the same ISP but 2 different routers, I would use local preference instead of wait to decide how I'm going to leave the autonomous system. We could load balance over the link as well. I like to use the term load share. BGP doesn't really do kind of dynamic load balancing, but we can do load sharing based on policies that we create in our BGP domain. Multi-homing simply means that we are connected to more than one ISP at the same time. We can have this for redundancy. We can have this for, maybe even possibly choosing a better optimal path. If one ISP is originating some prefixes and the other ISP has access to those prefixes, but they're not originating them. So we can choose a better path in that case. But it also gives us an ISP independent solution. If there's a problem within the service provider's network in a dual homed environment, it's going to affect both connections. But in a multi-homed environment, one service provider having issues would not affect the other connection to the other service provider. And BGP is definitely used a lot in this particular scenario. Dual multi-homed means that we have 2 connections to multiple ISPs. I don't know if they actually have diagrams that show that. No, they don't. But dual multi-homed would look something like this, where I would have, say, ISP A and ISP B. So that would be multi-homed, a multi-homed scenario. And then dual multi-homed would be something like this, right? Where I have 2 routers on my enterprise and they are redundantly connected to ISP A and ISP B. This would be the highest level of redundancy that we could have within our enterprise. But as you add, go from single home to dual home to multi-home to dual multi-home, you're talking about increasing the complexity of your routing decisions. How do I leave my enterprise? How do I influence how packets come into my enterprise? I have to be aware of or cognizant of the fact that I want to make sure that I'm not becoming some sort of transit AS for internet traffic and so on. But there's different BGP attributes that we can use to manage this process. Wait and local preference, multi-exit discriminator, that's an inbound attribute. AS path and multi-exit discriminator can be used inbound to influence how traffic comes into your domain, whereas wait and local preference are policies that we use to determine how we leave our autonomous system. AS path can be used in a sense that we can prepend our own autonomous system multiple times to lengthen the AS path to make it less preferred and so on. We'll talk about some of those concepts a little bit later on. All right. We understand why we would want to have this multi-homed or dual-homed or these redundant connections, obviously for redundancy, right? If one router fails in a dual multi-homed environment, if one of our routers fail within our enterprise, we still have the other router to rely on to be able to communicate to the service provider. If one of the service providers fails, or even some sort of path within the service provider fails, making that overall service provider less efficient, I can choose to route to the other service provider and so on. It makes sense why we understand why we would want to build this redundancy in. All right. It helps with local redundancy. It helps with redundancy in the event that a WAN might fail, a WAN circuit path might fail, or even a service provider issue might arise and a particular service provider is not functioning correctly. All right. Which option I decide to use will depend on several factors. Do I want high availability? Is that my only concern? Meaning that I have a primary path and I just want to have a backup path in case the primary path fails. Probably the easiest scenario to deal with BGP, because we don't have to have complex policy decisions that are made by the routers to decide what path to use. Am I doing some sort of load sharing? Load sharing is a term that we use that's different than load balancing. And I always tell my students this: load balancing, from what I've seen from Cisco documentation as well as other resources, load balancing tends to identify a dynamic scenario in which we're dynamically sharing the load across multiple links, whereas load sharing is more of a manual configuration, kind of like setting up multiple HSRP groups, hot standby routing protocol. So HSRP doesn't really do load balancing, but you can create a load sharing scenario by creating multiple HSRP groups and having different gateways for different clients in the enterprise and so on. Now, when it comes to load sharing, obviously it gets a little bit more complicated because we have to have a policy in place that allows us to identify which path is going to be used for which prefix destinations, right? Which destinations that we're going to. And we can use various path attributes to influence that decision. We can, we're receiving prefix information from the service provider, and we can create a policy within BGP that says, let's go ahead and modify the attributes of this particular prefix so that we're choosing path A over path B or whatever it might be. All right. The tools that we use to control the traffic flow are probably going to be things like route maps and various match and set conditions within a route map to change how we decide to choose one path over the other. For example, let's say it's AS path is the attribute that we're choosing, and I'm receiving prefix information about network X over two different ISP connections. Inherently, the AS path attribute is probably going to be different for those paths anyway, because each ISP is going to have their own autonomous system, but the AS path length might be the same. So I would have to make a decision. BGP doesn't load balance. It doesn't say, well, if all the attributes are the same, let's go ahead and use both paths. BGP doesn't do that. BGP always ultimately will select one path or the other. So the overall algorithm or the BGP path selection process will finally whittle down the choices to one, and it will always be one. But we can influence how those choices are made based on manipulating those particular path attributes, based on creating policy. And that's what is important in this particular case. The last circle is also very important. Use caution not to become a transit network. In a multi-homed scenario, it is possible, although a lot of mechanisms in place to prevent this from happening, but it is possible that you could end up becoming a transit AS, meaning that people on the internet are going to use your autonomous system to route from one service provider to the other. You become a transit network. The way that we prevent that from happening is we ensure that we're not re-advertising prefixes from one ISP to another. We use filters, prefix lists and filters and whatnot to ensure that we're only receiving the routes that we want to receive from the service providers, and we're not re-advertising those routes to the rest of the world so that we end up becoming a transit autonomous system. All right. So they have an example here, single homed BGP with multiple links. Now, this is interesting in this particular case. It's kind of interesting that they decide to use this as a particular example. If those were EIGRP links, or if those were OSPF links, wouldn't be a problem. We would basically load balance over those links dynamically, and we wouldn't have any problem kind of utilizing both of those links. In BGP, it's a little bit different, especially when we're dealing with eBGP across the network. Because eBGP has a hop limit that is predefined, a hop limit of 1. So eBGP peering relationships have to be direct and physical, and I would have to choose to peer over the top link, or I'd have to choose to peer over the bottom link. We can ignore that. We can ignore that value, or we can increase that value by using the eBGP multi-hop command, and then we would peer between the loopbacks. Now it's interesting that they show us running iGP as well in this particular case. I think that's just an example of, in iGP, with an iGP protocol, we could do load balancing, but not with BGP. Equal cost multipath routing, or even with EIGRP, unequal cost multipath routing is a viable option. Now, the other aspect I think that they're talking about here is peering with the loopback interfaces, which is why they highlight the loopback interfaces on the diagram. And that is actually typically what you would do in this type of scenario. You have multiple physical links between the eBGP speakers. You don't want to peer with one of those physical links, because if that physical link goes down, then the peering relationship goes down. So you want to peer with the loopback interfaces, but you have to have reachability to those loopback interfaces. And I think in this particular case, they're representing the iGP protocol to provide the reachability between the loopback interfaces, which then in turn would allow us to form that eBGP peering relationship based on those loopback interfaces. But in most cases, we're probably going to end up using some sort of static routing as opposed to some sort of iGP routing protocol. But there has to be reachability between the loopbacks. We also have to do an update source command. The update source command indicates the source address that we're using for the BGP updates and the BGP messages. Otherwise, the egress interface is going to be used as the source for those BGP messages. And because that's not how our neighbor statements are defined, we're not going to be able to establish a BGP peering relationship, because the BGP messages are coming from a different source as opposed to the loopback interface. All of this stuff is kind of related to actually configuring BGP and getting into the implementation of BGP, which of course we're not really doing in this class. I've mentioned that a couple of times already. Okay. Let's take a look at a couple of other scenarios here as well. Dual and multi-home BGP designs. In this top example here, we have load sharing capability. We have a single router that is dual homed, if you will, not multi-homed, because we don't have multiple service providers, but it is dual homed to the same ISP. And some of the attributes that I might choose to use in this particular case are, well, in this case, I really am kind of limited. I can use a multi-exit discriminator value to influence how AS456 gets to AS123, or I can use the weight attribute to influence how AS123 gets to AS456. I can also use the AS path attribute in either case, both inbound and outbound, to determine what path I'm going to use. Now, BGP doesn't do load balancing per se. We have the same ISP connection, two different physical circuit paths, two different eBGP pairing relationships, and we have control over how traffic leaves our network or how traffic comes into the network. Now, as far as influencing how traffic leaves the ISP and comes into the network, we have two options. We can choose the MED, or we can, which is an optional non-transitive attribute, or we can use AS path, which is a mandatory attribute, a well-known mandatory attribute. But in any case, these are only suggestions that we can send to the service provider. The service provider ultimately has control on how they decide they want to route outside of their domain. In other words, traffic leaving their domain. Now, generally speaking, the service provider will kind of agree or at least work with you on how you decide you want to route to your autonomous system. But ultimately, it's the decision of the originator of the data to decide how they want to leave the autonomous system. This particular scenario that we're looking at here demonstrates ECMP, equal cost multipath routing at the BGP level using the BGP multipath feature. As I mentioned before, by default, BGP ultimately will only come down to one path. We're going to choose one path among all of the different paths that are learned from the AS. And that's the standard behavior of BGP. The path selection process, the 13 or 14 steps, I think it's maybe 12 or 13 steps that we go through. We never really get down to the 12th or 13th step, but the 12 or 13 decision points that we use to make a routing decision ultimately results in a final decision made on how we want to leave the domain, okay? Or how we want to enter a domain or whatever it might be. And ultimately, that always ends up being a single path. We can change that behavior using the maximum number of parallel equal cost paths that are allowed by BGP by using the maximum paths command. And this is anywhere from 1 to 6 for IPv4. I think it's actually a higher number for IPv6. Typically, it's higher for IPv6, but the default maximum path value is always 1 in BGP. And we can override that and change that value. All right. But still, it is a load sharing scenario as opposed to a load balancing scenario. Here's an example. We have multipath. We have 2 equal cost entries in the routing table for all the prefixes that we're learning from ISP, from the ISP 456, right? And it's advertising the 198.51.100 prefix to AS123 over both of those eBGP peering sessions. Okay. Obviously, load sharing ingress path selection splits the address range and allows us to advertise maybe either more specific routes or maybe advertise what we call aggregate routes in BGP. But if you can't split the address range, we have to decide how we're going to reach that particular destination. I mentioned already we can influence path selection based on modifying the attributes, particularly ASPath or MED. Let's say, for example, I'm advertising the 128.66.00/16 prefix. And you'll notice here what they did in this case is they said, okay, we can do one of two things. We can either advertise the aggregate, which is this red one here, or we can split the network logically, even though we're not technically splitting it in our own domain. From the service provider's perspective, it looks like we'd have 2/17s. Obviously, in this particular case, the ISP is going to route to the 0.0/17 over the top link and to the 128.0 over the bottom link. If for some reason those prefixes are stop getting advertised, or maybe this link fails, we still have the aggregate that includes the 128.0/17. So we still have that redundancy in this case because the aggregate would be used. So that's one of the options. All right. But there's other ways that we can do this. We can do this by implementing attribute manipulation, like I said, MED or ASPath. When it comes to manipulating BGP attributes, we have attributes that will influence how we leave the autonomous system and attributes that will influence how we enter the autonomous, or how the neighbor enters the autonomous system. And the only two attributes that allow us to influence how the neighbor enters the autonomous system is something called the multi-exit discriminator and ASPath, right? So I might say, for example, advertise both of these prefixes over both links, but I'll make the ASPath longer for this prefix over that link, and I'll make the ASPath longer for that prefix over that length, assuming that the ISP is using the ASPath attribute to make the routing decision. They're not using local preference. Local preference is going to be selected before ASPath. Then we can kind of influence how the ISP decides to leave their domain. All right. But the key here is that, and we won't see the details of this, but again, an advanced routing class or maybe even enterprise core would talk about this in more detail, but we use these BGP path attributes to influence how we enter and leave an autonomous system. All right. And by the way, we still have the same golden rule, right? Longest prefix routing is always going to take preference over shorter prefix routing. That doesn't change regardless of the protocol that we're using in this case. Here's an example where we have dual homed connections to one ISP with multiple routers. In this particular case, again, because we have a different physical topology, we might have to use different attributes to decide how we're going to route. So in this previous example, leaving autonomous system 1, 2, 3 could be achieved, deciding how we're going to leave autonomous system 1, 2, 3. If the ISP is advertising a subset of prefixes to us, could be done using the wait attribute. It could also be done doing AS prepending on the inbound path for the routes that we're learning from that ISP over those particular circuits. But in this particular example, a wait attribute would not be useful because we have two different routers. So we would have to use local preference in this particular case to be able to decide how we're going to leave the autonomous system. All right. Let's see what they mention in the book about this here. Load sharing and ingress path selection splits the address range. So again, same scenario here. The only difference is we're doing it across two different routers. So it says 50% and 50% in the diagram. Well, it actually says it in the next diagram. Let me move down to that next diagram right here. Right? 50% and 50%. But is that really 50% and 50%? I guess it would depend on how many clients you might have associated to the 0.0/17 prefix, how many clients you might have associated to the 128.0/17 prefix. But again, this is load sharing, not load balancing. We're not doing like a per packet load balancing type of scenario. So you would have to understand what the traffic flow looks like in your environment to be able to understand what the effect of the policy configuration might be on the traffic load and the traffic loading conditions that might exist on the network. All right. Let's see what they say here. Load sharing and ingress path selection splits the address range or advertises both with more specific and aggregates. The aggregates are important here because if for some reason one of these links fails, we still want to be able to route. And the aggregate is what allows us to continue to route. But because we do longest match routing or longest prefix length routing, we can still influence the specific path that's being chosen based on those longer prefixes. If the address space cannot be split, the AS path prepend or MED can be used. So again, trying to influence how the service provider decides to route to our 128.66 subnet. AS path prepending is where we make the AS path longer by prepending our own autonomous system multiple times. As the originator of the route, we can do that. So maybe I insert my AS 3 or 4 different times to make the AS path longer, or MED, a multi-exit discriminator, is a numerical value that we can assign to prefixes that we're advertising. And the service provider can choose to use that value that's being set by us to make a routing decision. But it is an optional non-transitive attribute, so the ISP could actually technically just ignore it. Okay? So a lot of options with being able to kind of identify how traffic comes into our network and how traffic leaves our network. All right. Here we have a multi-home scenario, 2 different ISPs and a single router. Now this is interesting because in this particular case, a little bit different than the first scenario we saw, which was a dual homed scenario, right? Single router, dual homed scenario, as opposed to multi-homed. ISP1 may have or may own a bunch of prefixes that we want to route to. And we may request that ISP1 advertises those prefixes to us so that we have a specific route for those destinations as opposed to using a default route for ISP1. And then conversely, ISP2 would do the same thing. But ultimately, for the networks that ISP1 and ISP2 don't own directly, and they're just simply connected to the internet, and they have some reachability to network X in this particular case through the internet, we have to decide which path we're going to use. Now, typically this will boil down to, your standard cost benefit analysis, right? AS path is, we don't use traditional metrics in BGP. So AS path would probably be my first deciding factor in that particular case. Because as that network X gets propagated through the internet, each of the autonomous systems that are associated with network X are going to get added to that path, and we'll end up selecting the shortest AS path, which actually may not be the most efficient path from a bandwidth perspective, but we don't use traditional metrics with BGP. But just like anything, we have different options for, just like all the other scenarios that we've walked through, we have different options for deciding how we're going to leave the autonomous system and how we're going to allow traffic to come into our autonomous system. So the consideration that we decide to use, are we going to use the weight attribute? Are we going to use AS path prepending to influence one path being selected over the other path? Are we going to do that inbound versus outbound? Are we going to have provider independent address space? And we now have to advertise this address space to the service providers. And when we advertise the address space to the service providers, are we influencing what that address space looks like? Maybe we prefer to receive all of our traffic from ISP1 and we only have ISP2 as a backup in case ISP1 fails. We would want to make sure that when we present our prefix, our provider independent address space to the service providers, that we're providing attributes that will allow that to happen. Okay. How do I load share across this scenario? It looks much like it would look in all the other scenarios, right? We have an aggregate route that we might send out. And we have the kind of more specific routes that we might advertise over individual links. We might also be receiving routes from the service providers. In this particular case, the blue line or the blue arrow represents prefixes that ISP1 is responsible for. And the reason we have a red X on that blue line going out to ISP2 is that we don't want to re-advertise those prefixes over to ISP2 for the fear that we may become a transit AS. People in ISP2 may decide to go through us, AS123, to get to those prefixes that are being originated by ISP1. So we would only advertise our provider independent address space. We would not advertise the prefixes that we're learning from the other providers to the providers. Okay. To load share for the ingress path, for the egress traffic, it may be simply because maybe a way that we do that by applying different attributes to the routes that we're learning. Certainly, if it's internet-based routes, right? ISP1 has, say, network A, B, and C. And ISP2 has network X, Y, and Z, okay? But there's a peering relationship either directly or indirectly between ISP1 and ISP2. So ISP1 knows about network ABC because it's originating those prefixes, but it also knows about X, Y, and Z because it has a relationship with ISP2 over the internet, and vice versa, okay? But knowing that prefixes X, Y, and Z, in this case 1 to 128, excuse me, let me keep everything together. Prefixes A, B, and C on ISP1, in this case 1 to 128, we want to make sure that that is the preferred path, that top link to ISP1 for those prefixes. So as those prefixes are being advertised into my domain, I'm going to apply attributes to those prefixes that would make them more preferred over the prefixes that are being learned from ISP2. And there's different attributes that we can apply. Probably the most common is just simply the ASPath attribute. But we could also apply weight values in this case because we have a single router that's multi-homed. But we could apply a weight value. That is a Cisco proprietary attribute that allows us to decide how we're going to leave an individual router towards the service provider destinations. So I can apply that. Most likely it would be ASPath. ASPath is one of the most commonly used attributes to make a selection on how we're going to route, and vice versa. So maybe the 129 to 254 networks are being serviced by ISP2. We could still technically get to them through ISP1, but we would have to go that way. But I'd rather just go that way, right? So again, we're just trying to make it so that the 129 through 254 networks are more preferred over the bottom link as opposed to the top link. And that's the whole point of BGP. BGP is a path vector protocol. It uses path vector attributes to make routing decisions, okay? And we have the option of influencing how those routing decisions are made based on manipulating those particular attributes, okay? So our last example is multi-homed with 2 ISPs and multiple local routers, the most redundant option that we have. And honestly, it's not really that much different than what we just saw, the single multi-homed environment, where we have a single router multi-homed to 2 ISPs. The only difference is we have to decide potentially how we're going to leave our corporate network. And instead of using like a weight attribute, we might choose to use a local preference attribute instead. But again, ASPath would work great in this particular scenario. So the design is going to look pretty much the same. We're going to have the same concepts. We split the network, possibly, at least logically split the network. So it appears that we have 2 different subnets. We simply advertise those prefixes. And then for the inbound side, again, we can apply different attributes to influence how we leave the network for those destinations. So it's really no different in this case than what we saw previously. The only difference is there may be another type of attribute that we might want to use to influence how we leave our domain, our autonomous system. So if we have a scenario we want to try and get 50-50 load sharing, or even have preference routing based on the prefixes that originated by the service provider, we would still be applying the same types of attributes. But you have to keep in mind, and we haven't really talked about this, some attributes are transitive, meaning that they move from one BGP router to the other, and some attributes are non-transitive, means that they only go to the neighbor and they don't go beyond the neighbor. So we have to make sure that we choose the appropriate attribute based on what our goal is in the design. All of this is done, by the way, influencing BGP path selection by using policy-based routing, essentially route maps with match and set conditions on peering relationships. We apply the route maps to the peering relationship, and then based on how the route map is configured, we can influence these different attributes that are being applied to those BGP paths, to those prefixes that we're learning through BGP. All right. So that pretty much concludes this discussion of our kind of basic BGP routing and redundancy scenario. We talked about clustering, we talked about route reflectors, we talked about the different topologies, the limitation of iBGP and the concept of BGP split horizon. We're going to get into another discussion now about BGP, where we're going to talk about address families, we're going to talk about attributes, and finally, we're going to get into the discussion of the BGP route selection process and the BGP preferences. And then we'll do BGP communities, which again is another option for creating that ability to share information and dealing with split horizon issues in BGP. We didn't get into that in this section, but we'll see that in the next section. All right, so we'll see you guys there.